Good afternoon, everyone. I'd like to welcome everyone to today's webinar, Mechanical Issues Can Lead to Electrical Faults. Today's webinar is presented by Joe Gierlach from TEG Corporation and hosted by myself, Doug Wagen. So again, I want to welcome everybody, especially those who are just tuning in. As always, you can look forward to just about every month UE Systems putting on one of these educational webinars. In this case, it has to do specifically with airborne ultrasound equipment for electrical applications. But you'll notice as the year goes through, we also like to deliver some value by having webinars that aren't necessarily just about ultrasound. Sometimes the webinars have to do with other technologies. Sometimes they have to do with processes, systems, anything really to add value to your overall maintenance and reliability programs. So as we get started here today, a little bit about UE Systems for those of you who aren't familiar with us. UE Systems was founded in 1973, so 35 plus years experience with ultrasound. Pretty large global footprint. We've got offices all over the US. We've also got international support for those of you who are logging in from other countries other than the US. As you can see here, our corporate headquarters is here in Elmsford, New York, right about 20, 30 miles north of New York City. We've got regional support headquarters, which have both technical support and training staff located in those areas in the green stars, and then our regional support offices are in white. So again, a pretty large global footprint. Wherever you're at, we should be able to offer you the kind of support that we've become known for and that you've become accustomed to. So anyway, I'm going to go ahead and welcome Joe Gierlach here of TEG Corporation, and he's going to talk to us a little bit today about mechanical issues that can actually lead to electrical faults. So Joe, welcome. Thanks for being here.
Thank you, Doug. I appreciate that. Well, good afternoon, everybody. I appreciate you joining us. And as Doug said, my name is Joe Gierlach, and I am from a company called TEG Corporation in Pittsburgh, Pennsylvania. And I am in charge of the operational technical training and support division of our company. And to just preface what we will be talking about today, I've entitled this Mechanical Issues Can Lead to Electrical Faults or Cause Electrical Faults, particularly focusing today on high-value assets and the scrutiny they demand from a maintenance standpoint to foster reliability. First, we'll tell you a little bit about our organization. We are a licensing business. In other words, we sell franchises, electrical contractors. And one thing they always ask us is, what does the word TEG mean? It really comes from a derivation of another word, but it doesn't really have a meaning. It is a trademark or a brand name for the services that we are providing. And the philosophy at the founding of the company was the word TEG comes from integrity. And the philosophy behind that was, just as the integrity of the customer's electrical systems is critical to their operation and business, so is the integrity of the electrical contractor that they're employing to maintain their systems. So our organization came into being. We incorporated in 1992. And select independent contractors get awarded a license and the right to use what we call our exclusive business operating system that consists of these 10 components here. As a statistic, here in the United States, there is over 68,000 electrical contractors within the continental United States, and less than 1% of those qualify through our screening process to become part of our organization. Back in 1992, TEG incorporated under the ownership of Sargent Electric Company in Pittsburgh, Pennsylvania. And Sargent has a very large electrical contractor who's been around for a number of years, specializing mainly in heavy industrial, and they believed in this concept and founded the company, which later became TEG Corporation. In 1996, Johnson Controls, who a lot of you are probably familiar with, acquired 50% ownership in our company. So it was a joint venture at that point. And then finally, in December of 1997, Hartford Steam Boiler, who has been insuring boilers and infrastructure since 1866, acquired a third ownership. So up until recently, we were jointly owned by these three companies. As of today, we have a presence or a footprint as well in over 300 cities around the globe, in approximately 120 locations. And UE Systems has been a wonderful partner of ours, and their large global footprint certainly plays into where we have been expanding, and we work together on growing both of our businesses. So it's a win-win for both of us. We're proud to be the largest, most professional electrical service organization in the world. Currently, we are in 25 countries, and that's rapidly growing. In the next 5 years, we plan to hopefully double that. So we will continue to grow and increase our footprint across the globe. And the main thing we pride ourselves on from an organizational standpoint is we guarantee our electrical service. And there's no equal to that as of today. Whatever we service, we have the ability to guarantee against failure. And with our contractors, customers, that means if we're maintaining something and have ownership and there's a failure, it will be replaced at no cost to their customer. So with that, let's talk some ultrasound here. I'm going to focus today on a singular component within the electrical system, a transformer. And we all know that this is probably one of the most critical components in the electrical system. Large or small, there are many other items and systems and operations that could and would be affected by the failure of a transformer. Most often, they are not readily available in the event that it fails. As time has gone by, the availability of transformers as far as replacements and their lead time has exponentially increased. And that's getting tighter and tighter for a number of various reasons as time goes by. It's not going to matter if we are discussing a liquid-filled unit or a dry-type unit. The reality is maintenance is key to longevity, as we know, and the components within these units are essentially the same. So the same principle of operation, the same maintenance considerations, the same failure points. In today's example, it's going to involve a unit that's very similar to the ones you see pictured here. It's a unit substation in a hospital in the state of Ohio, and the service initially was performed in October of 2011. This transformer had been installed at the time approximately 5 years, and it wasn't very old, but being in a hospital, a critical component nonetheless. The energized services that our contractor performed began in October of 2011, like I said. This was the second time they had visited this customer site, and these assets were under a maintenance agreement. And on the previous year's visits, everything had received a clean bill of health, so there were no deficiencies documented. The technicians obtained recordings of each one of the windings of this unit in question, along with a comparison unit that was sitting adjacent to the one in question. In this particular case, we have two units that are identical as far as manufacturer, as far as rating, loads being served, and load level. So with ultrasound, it is always important whenever possible, and particularly in electrical applications, to utilize comparisons. They can be very telltale and give us a good starting point. Just to give you an idea of the initial recordings that October, I'm going to play you a wave file from each winding. And on the A phase and the C phase of the windings, you will notice there's hardly any emissions whatsoever, as would be expected. And here's the A phase. Now I'll go ahead and play the C phase so you can see it is very similar in nature. And finally, on the B phase, this is the one that caught their attention. Now, from a quality standpoint, it's very evident that there are differences orally to these recordings, not just from an intensity or decibel level, but the quality of the sound. With transformers and magnetic lines of flux, there's inherently a 50 or 60 hertz emission that's created, but that particular recording had additional components superimposed on top of it that we'll talk about here shortly. Now, if we listen to the sister transformer sitting adjacent to it, all three coils are what one would expect on this type of unit. First, the A phase. Now the B phase. And finally, the C phase. So those are all good quality, uniform, and consistent recordings. Typically what we would expect on this type of dry type transformer. Now, looking at the Spectralizer software with the recording that was made on the suspect transformer and the sister unit, you can see that the FFT has a comparison between the two B-phase coils. And this is a 60 hertz system for our friends overseas, so I have the harmonic cursor set to 60 hertz. And we see some activity there present with the red trace, the suspect coil, compared to the sister unit, which is a lot quieter or lacking in activity compared to the red trace. On the time domain, one of the things we look for that's very typical with the instrument itself and this type of electrical component is down the center of the axis, you have the broad band of white noise. And then we are on the lookout for deviations from that broad band, which would represent either electrical discharges or some type of mechanical vibration or looseness. And in this illustration, the key thing that sticks out is we have deviations or excursions from that base broadband noise that are varying in its amplitude across this half-second slice of the recording. So we have something changing in intensity that's either a discharge or some type of vibration. On the sister unit that was sitting adjacent, you can see clearly there are no deviations from the instrument noise, which indicates the complete lack of any type of discharge, mechanical vibration, or loose components within that unit. This is what one would expect on a properly functioning device. By slicing up or magnifying the view of the suspect coil, you can see even clearer the differences in the amplitudes on these peaks, as well as some variation in the timing. In other words, the spacing between where these excursions or deviations take place. That's important when we talk about the timing of an electrical sine wave, because everything is very predictable on 50 and 60 hertz systems, and when we begin to have faults, the timing of those excursions can be affected, which is what the time domain tool is very good at illustrating. Now on the FFT, going back to that, we can see that there are some what's called fault frequencies, but notice they are not taking place on the 60 hertz harmonics. And this is important because electrical faults, when they occur, will have these fault frequencies take place on harmonics of 50 or 60 hertz. When they shift off of that frequency, that leads us to understand and believe it's not going to be specifically electrical in nature. But there is an abundance of frequency noise throughout the spectrum. The activity taking place in between each one of the harmonic cursors does indicate something is occurring with this unit, but we're just not completely sure at this point. The other thing is turning the 30 Hz harmonic cursor on is an important analytical step. And you can see where the red arrow is pointing, there is a peak, although it's on the negative side here, I call it the negative side, at 30 Hz. One of the key indicators that we have a mechanical issue, not an electrical issue. When we're dealing with electrical, you will never have a faulting frequency below your line operating frequency if it is mechanical, if it's electrical in nature. We can see this is half of the operating frequency is 60 Hertz, which now points to a mechanical issue. Just to give you an idea of the type of unit we're dealing with here, this is basically a square D manufactured transformer. It's 2000 kVA. It's air-cooled with a temperature rise rating of 115 degrees on the winding insulation. The high side is 12,470 volts. Low side is 480-277, three-phase. It's rated at full load for 2,400 amps and has an impedance of 5.76%. If we look at the bottom two data fields here, you will see what I'm calling the good and the bad transformer, and you'll notice that the load demand on both units is very similar in nature. So we have the same types of current loading on each unit, but we have a qualitative difference on one of the coils with the bad unit. Now, another indicator that we found pointed to something going on was the infrared image. Everybody's familiar with infrared. It's a great complementary tool, widely used. And looking at the left side, what I call the good transformer, this is the horizontal core piece coming up through the winding, and you'll notice it's measuring a temperature of approximately 155, which is not uncommon to have these core temperatures run higher. But you'll notice on what I call the suspect coil, the dynamic range of the camera is exceeded. It's greater than 150 degrees C, and the camera can't quantify that. You'll also see there's some saturation in this image showing where the temperatures are higher than the camera can measure. The important thing is looking at the direction of the thermal or heat transfer. It is coming from down inside the device. That's interesting because we have winding insulation down there, we have shims and supports. This is the type of stuff, if it begins to move, it can begin to cause damage to the winding insulation. With this evidence and supporting data, we recommended a shutdown to this customer, which is not always easy when you are dealing with a hospital, as you can imagine. This would allow us to have further diagnostic testing on it, as well as getting it all opened up and doing a thorough visual inspection to try and determine the root cause of both the ultrasonic emissions and the elevated thermal energy present on that one coil, because that was what we were after. The electrical tests would be necessary to determine if any damages occurred are the typical ones one might use on this type of equipment. They would include insulation resistance on the winding insulation, the winding resistance measurements, the turns ratio values for the coils within the transformer, as well as power factor dissipation testing. In other words, tan delta, finding out how much watt loss is occurring through the winding insulation, which could be a measure of degradation. The electrical tests that were performed by a third-party company revealed no notable abnormalities, and most of them were within the industry standard limitations. Shown here are the winding resistance measurements. They're all within 1% of each other, which is acceptable. The insulation resistance, or what some people call megaring, and showing what's called the polarization index. This test is done by applying a test voltage for 10 minutes and then recording a 1-minute value and taking the 10-minute value that's measured, dividing it by the 1 minute, and that gives you what's called your polarization index. Typically, we like to see this well above 1, and as you can see by the results, the lowest PI value is nearly 4. So the insulation at this point is pretty good. The turns ratio has very tight tolerances, and as indicated here, the calculated ratio for these units, as well as the measurements of the adjacent coils, should not exceed 0.5% between each other or the calculated ratios. And these values here clearly indicate we're within specifications on both the high and the low side windings, so there's no turn-to-turn shorts at this point within the transformer. The power factor dissipation measurements were within the NETA specified limits, and it does not indicate any type of excessive loss related to watts through the insulation at this point. Now, there are some losses which indicate a marginal degradation. It's not nothing that would be taking the unit out of service or rewinding it at this point, but keep in mind we're trying to be both condition-based and predictive with these units to plan repairs as opposed to allowing it to fail. Upon opening the unit, this is a visual image of where the suspect winding infrared image and recordings were made prior to the shutdown. As we get deeper into this, is it good news or bad news for the customer? Well, this is a yes and no answer based upon what was revealed. The item of interest here is what's called a miter joint, and some of you may be familiar with the construction of a transformer, but the miter joint is what joins the horizontal and vertical sections of the core within these types of transformers. So this is what we're looking at both on the A-phase coil and the B-phase coil. Now, it may be a little difficult to tell here, but there's a major difference that we're going to find out is going to be the root cause of our problem. On the A-phase coil here, the top left call-out shows the welded retaining strap to tightly join this vertical clamping steel with the horizontal piece. This is welded in place at the time of manufacture, and you can see the vertical clamping steel on the outside phase of the low voltage side to the right, and the horizontal steel is indicated by the bottom call-out to the left. This is all nice, even, flush, uniform, and a really good weld. It's the integrity of this type of joint that we would like to see. So everything here on the right-hand side, there's no differences in elevation, there's no cracks or breaks in the weld. The integrity of this joint is very good based upon the visual inspection and the electrical tests. On the suspect coil, though, we can see in this image, if you look closely, there is clear evidence that the horizontal steel is not flush with the vertical steel here where the weld is made. This is causing the top horizontal section to bow out on the low voltage winding on the B-phase side. And right where the call-out arrow is pointing, you should be able to see the elevation difference between the two pieces of steel. This is a problem. This is also exactly where the ultrasonic emissions that we recorded were originating from, as well as where the thermal energy was evident with the infrared camera that we saw earlier within the phase. And the intensity was at its highest point right in this general vicinity. So we are on to what is the cause of this problem. Once we started looking at the laminations within the core, we saw the visual evidence of this heating. Of course, we saw it with the camera as well. But you can clearly see the blackened area on the core here with the vertical laminates where the thermal energy was present. And that backs up more or less what we were seeing with the infrared camera. So there's already thermal damage that has taken place within this transformer. Now that in and of itself is not enough, again, to pull the unit out of service, replace it, recondition it, but we can see that damage is occurring, and this is validating what we recorded with the Ultra Probe. Looking at the top section, the laminate separation is even more clear. Right where the technician's finger is pointing, you can see the separation between the steel and the laminates there. That should be nice, tight, snugly fit up against there to contain the magnetic lines of flux. For perspective, what was able to take place on this particular gap, you were able to take a flathead screwdriver and with ease stick it down into this opening. So the separation was not minor by any means. It was moderate to severe at this point. From a different perspective as well, or a different camera angle, you can see deeper into the core, the laminations were already beginning to separate within this core. And when this happens, you no longer have that bond between the pieces, and with the expanding and collapsing magnetic field, these laminates begin to vibrate. When they vibrate, they generate ultrasonic emissions, and they cause thermal heating. So this is getting closer to the source of what the issue is here. Another view of the core clearly shows the heating damage based on the thermal effects of the energy being generated, where it was literally bubbling up the varnish that was on the core. Because they dip these things in varnish at manufacture, seal everything up. That was starting to peel off due to the heating effects. Because this miter joint that connects the center phase to the top horizontal laminations is no longer connected properly, based upon this image I showed you earlier, where there's an overlap and a bowing of that joint, it can no longer contain the magnetic flux path, and it interrupts and disturbs it, and this would become the most likely cause of both the ultrasound and the additive heating effects. If you cannot contain the lines of flux within the core, you will get these effects, and both technologies can and do point this out, but without the benefit of the ultra probe, this may have gone unnoticed, but thankfully it was found. The sister unit that we listened to earlier for the comparative recordings was also examined at the time of the shutdown, and what we saw was that it was exhibiting signs of cracking in the varnish already. And on this image, you can see the cracks toward the top center of the image, but there's no separation here at this point. That is not to say that this will not occur in the future, as these units were of the same generation, and remember, they are running at the same loads in the same environment. So it's being exposed to the same things, and already there's early evidence we're going to see the same delamination of the core within this unit, and it could possibly be the same defect in the manufacturing with the miter joint that we've seen earlier. So it's safe to say it's going to be subject to the same problem as time goes by. Finally, a follow-up visit came a full year later, and with consultation back and forth between the manufacturer and the customer and trying to determine what to do, it was decided that the best thing was to take this unit out of service and remanufacture the horizontal vertical miter joint to ensure that it had a flush fit and would contain the magnetic lines of flux. This course of action was deemed necessary and a prudent response, because after a year, based upon this recording, it was clear the situation was deteriorating and time was of the essence to get a repair. So this, you will hear, not only the tonal and aural quality of this recording is noticeably different, but the sound intensity level has become even greater. So it's only a matter of time before there is an electrical fault or failure within this unit, and that has been acknowledged by both the customer and in some ways the manufacturer. This will lead to issues not only with the core but with the winding insulation. It could cause some type of fault which damages the windings, or worse, it could cause a failure of the unit. So there is a plan in place to address this unit, because this recording was only a couple of months ago, And when I get further details on the outcome of those repairs, I would be happy to share with everybody. But the moral of the story is, without the benefit of the UltraProbe, something like this can and does go unnoticed in a lot of cases. What I played for you on these WAV files was not audible to the human ear. So that is the benefit of using this technology in conjunction with others. It is a very important part of what we do at TEG Corporation. It has always been our primary tool along with the infrared camera, and it will always continue to be that way. So we were proud and happy to identify this fault, to save the customer grief, address it before it became a very expensive issue to fix. So with that, the guys will take some questions if you have them, and you can send them to me after this webinar. I've listed my email address here at jgierlach@teg.com, and as they come in, I will do my best to answer them.
Folks, Joe still has a couple of minutes here with us. If you'd like to type in some questions, I'd be happy to pass those on to Joe, and we can see if we can get some of those answered live and online here.
Sure.
As Joe said, he's got his email address there. If you prefer to send those personally, you can certainly send them to Joe, or you can send them to info@uesystems.com. We'd be happy to get those questions answered for you. All right, we've got a couple of questions that have come in here, Joe.
Okay.
Let me go ahead and see if I can ask a few of them. What was the timeline from the initial testing until that unit was removed from service?
Well, that's a good question. And the unit was monitored regularly after identification of this fault, but the timeline between the initial discovery, the third-party testing involving the manufacturer, and getting the initial shutdown to identify these faults was less than 90 days.
Okay. Another question here on that miter joint seemed flush in the PHA. Why was there cracks in the varnish?
PHA winding, let me see if I can pull that slide back up. Are we talking about this slide?
Hold on, we're going to give back his
okay.
slide here. We've got to give back the screen to you.
Oh, okay, that's right. All right, we talking, let me find the slide. This miter joint here?
I think so. I don't have the ability to real-time have
okay, no worries.
Question, Joe.
So we had a comparison between this miter joint, which was on the B phase, and the A phase right here. And this isn't necessarily showing the varnish on the laminates, but if I go back to this slide here, down on the bottom of the screen where the horizontal piece comes up from the winding, the thermal energy was transferring down into the winding and onto the core laminates. So the heat transfer caused a chain reaction effect on the bubbling or the beading of the varnish here on the core.
Okay.
I hope that answers the question.
And if not, the asker of that question can certainly send you an email. Hey, I got another good question here. It's sort of a two-parter. How old is the transformer, and how do you handle the arc flash hazard when you're examining this type of unit?
Well, that's a great question. And in the first part of that question, how old was it? The transformer was only 5 years old, which was disheartening and alarming to us. Second of all, this particular facility had actually performed their arc flash study, and due to engineering, implementing engineering solutions, the incident energy here was acceptable for the protective clothing that's available today for arc flash.
Okay. And another question here, is it possible to use the ultrasonic probe, or in your experience have you used the ultrasonic probe to pinpoint the mechanical failure location in this case?
This got us in the general vicinity, but it leads us to where the faults are by combining all the other testing and technologies to pinpoint it down. The directional nature of the ultrasound makes it good for getting fairly precise, but it doesn't tell us the root cause. In this case, using the airborne and the contact module, we were to get really precise as to where the emissions were originating from, and verified that once we got the shutdown with the visual inspection, the thermal inspection, and backing it up with the other electrical tests.
All right, cool. Another one here, Joe. Do you know if the manufacturer in this case conducted a root cause analysis? I mean, did they figure out what the cause of this was? Was it poor manufacturing, poor workmanship, materials? You know, what did they come up with?
At the last time that I received information on this a couple of months ago, there were two theories. Number one, there was a manufacturing defect on the core laminates prior to dipping and baking, and the other hypothesis, which is still being investigated, is a misalignment upon joining the horizontal and the vertical core pieces with the miter joint. At this point, the primary suspect is a manufacturer defect.
Okay. Okay. I don't know if I asked this one. How did you handle the arc flash hazard when you were examining this unit?
Yeah, the arc flash hazard analysis had been conducted at this facility, and for this particular unit, after employing some engineering mitigation, the hazard risk category was a number 3. The energy was reduced to about 24 cal per centimeter square, and we had dressed out, or the technicians did, in category 4 apparel just to err on the high side of caution.
Excellent. Well, thanks, Joe. Certainly, you're welcome to continue to put your questions in. And as I said, you've got Joe's email address, which you can send to send emails directly to him. You can also send emails to info@uesystems.com. Not only is a more detailed explanation of this presentation going to be featured, but Joe has some other electrical case studies. He's going to be doing a 2-hour workshop down at Ultrasound World 8 in Clearwater Beach, Florida in May. For those of you who are not familiar with this conference, this is basically an ultrasound users group meeting where we have anywhere from 100 to 120 users of ultrasound present. We have 15 or so presentations, some workshops, and it's a great opportunity to learn more not only about electrical applications for ultrasound, but how people have implemented ultrasonic programs, how to use it for condition-based lubrication, leak detection, energy management, and so on and so on. So, please take a minute to check our website out for more information on this important conference coming up in May, as well as for some other information on any of the aforementioned applications. Stay tuned for our next webinar. We try to put a webinar on each month, so in the next week or two, you'll probably see an email coming out on next month's informational webinar. This presentation is also going to be available on our website probably within a week. So if you missed it or you want to pass this valuable information on to colleagues and friends, certainly feel free to give them the UE Systems website. And again, it'll be available for full viewing with audio. So that said, Joe, thank you so much for your time and information today. Certainly appreciate it. Anyone can get questions to us. We'd be happy to continue to answer them online. Thanks, everyone. Have a great, safe day. We'll see everybody soon.